Hi everyone. It was a quick break, but I hope you managed to just stretch your legs, grab a coffee. I topped up the water. We're now moving into the final session of the day. And I think it's going to be a really great one. It's one I've been massively looking forward to since we first started planning this. We're going to have Kristin Sainani from Stanford University, who is going to talk about her wish list for improving the quality of statistics in sport and exercise science. I think, Kristin, as far as I'm aware, it was slightly before I started, you were one of the very first people to deliver a session for STORK right at the very beginning. And to date, it's still one of Vanessa's confirming you are the first. And to date, it's still one of the most popular and viewed sessions that we've had. So I think it's really, really great to have you come back. Most of us will know Kristin from her work, both in terms of science communication and writing, and also statistics and all of the other fantastic work that you do. Kristin, thank you so much for taking the time to come here today, and over to you.
Thanks so much, Amir. Thanks so much for inviting me to come talk. So yes, I'm going to talk a little bit about the things I wish for in terms of improving the quality of statistics in sports science. I will start here, though, with a couple of examples that I wanted to share with you. So this is an interesting example. What you're looking at here is a scatter plot from one of the top cited meta-analyses in strength and conditioning research. And what you're looking at is these dots represent athlete groups rather than individuals, because this is a meta-analysis. The point of this study was they were wondering if you improve your lower body strength, does that improve your sprinting ability? So they were looking specifically for studies where the athletes had all undergone an intervention and they had had their sprinting ability and their squatting ability measured before and after. They report that there's a correlation between improvements in your ability to squat and improvements in your ability to sprint. Now, the interesting thing is that actually there are several problems with the statistical analysis in that paper, and some of them are actually visually apparent on this scatter plot. I'm hoping that most of you can see one of the obvious things. I'm just going to focus on the most obvious, what I think is the most obvious of the issues here. But hopefully you'll notice this data point up at the top, which is up in the left top hand corner, which the researchers who sent this to me, Sophia Nymphius and Daniel Kadlec, called a rogue data point. And I just love that description because I think that's very apt. That is indeed a rogue data point. So there's this outlier way outside of the range of values for everybody, all the other data points on this plot, which should probably have caught the attention of somebody, either the editors screening this paper or peer reviewers or all the people who have cited this paper since, but somehow it was missed. And that's a little surprising because if you just take, a few seconds to step back from this graph for a minute and say, well, what does that data point even mean? What does that number mean? It turns out that data point is pretty ludicrous at just face value. So what are we looking at here on the X and Y axis? These are effect sizes. And so the sprint effect size is telling you about the improvements in sprinting ability. Negative numbers are good because you want to get faster. On the Y axis, it's telling you about the improvements in squatting ability. Positive numbers are good. You want to be able to squat more weight. But what are the actual units? Like, what do these numbers mean? What does 12 or 3 mean? So these are actually Hedges G effect sizes, meaning that we are taking like the mean squatting ability after the intervention, we subtract the mean squatting ability for the group before the intervention, and we divide by the standard deviation. That means our units are standard deviation units. So if we look at the coordinates of that rogue data point, the coordinates are 5 and 15, which in words would translate to that the athletes had improved on average about 5 standard deviations in sprinting ability and almost 15, I'm rounding up a bit here, but just for simplicity, almost 15 standard deviations in squatting ability. Those numbers should jump out at you as being highly, highly implausible. In fact, they are implausible at face value. Now, for those of you who maybe don't think yet in standard deviation units, hopefully if you're doing research for a while, you'll eventually think in standard deviation units. But just to give you a benchmark for what that looks like, I'm going to reference you back to the normal curve. Not everything, of course, is normally distributed, but just as a benchmark, this can help you to kind of get a sense of how big a standard deviation unit is. So thinking back to like a regular normal curve, if you are 3 standard deviations below average on a normal curve, that's going to put you in like the lowest 0.2% of the population. If you are 3 standard deviations above average, that puts you in the highest 0.2% of the population. So if we were talking about an effect size of a 6 standard deviation improvement in a group of athletes, that would literally mean that we were taking an entire group of athletes and moving them from the very bottom of the distribution to the very top of the distribution. That's for an effect size of 6. That's obviously highly implausible. Think about it, an effect size of 15, that would mean you're taking an athlete who are way in the tail of the distribution, and you're somehow moving them so they are all way up in the top of the distribution. So highly implausible. To think about it a little bit more, we actually pulled the underlying paper where that data point came from. And you can see in that paper that at baseline, that group of athletes was squatting an average of 123 kilograms. The standard deviation in that squatting ability was 8 kilograms. So if they improved by 15 standard deviations, that would mean that they improved by 15 times 8, basically doubling on average their squatting ability. And I think the intervention was maybe 8 weeks. That is clearly impossible. So this should have jumped out at somebody to say, hey, that data point doesn't make sense. And of course, that data point has a big influence on the entire meta-analysis because outliers often do have a big pull on the regression coefficient or the correlation coefficient. So what went wrong? You might be able to guess this. If you've been doing review as long as I have, you may have seen this error before. I've seen this in review many times. But what went wrong, that data point is definitely an error. It's a mistake. When the authors of the meta-analysis pulled that underlying paper and extracted data from the tables reported standard errors rather than standard deviations. And unfortunately, they either didn't recognize that that was the case or they didn't think carefully about the difference between standard error and standard deviation. But they just plugged the numbers into that effect size formula, out came 15 and 5, and they put it in the paper without thinking about it. Sadly, this error is pretty common. So we actually identified a number of other statistical problems in that particular paper, Daniel and Sophia and I. And so then we thought, well, let's go systematically review other meta-analyses in strength and conditioning research, which is their field, to see how often these different errors occur. And so we systematically reviewed the 20 most highly cited meta-analyses in that field from the past 20 years to look for these errors. And we found that all of them were quite common. And in particular, this standard error, standard deviation mix-up in the effect size calculation. We looked at 20 papers. There were 5 papers where we couldn't evaluate whether that error had occurred because they didn't actually report individual effect sizes. But of the remaining 15 papers, 9 out of 15 had at least one effect size reported where the authors of the meta-analysis had accidentally put standard error rather than standard deviation in the effect size formula. Well, that in many cases makes a pretty big difference. And I'm going to show you a few more examples of some of the papers we reviewed. I think it doesn't take a degree in statistics to catch the errors in these. So here is one of the most highly cited meta-analyses in strength and conditioning research. What you're looking at is one of the figures from the paper. So they were comparing plyometric training to a control group. And you're looking at a forest plot, obviously. They looked at a few different outcomes. So if you just look at this for a minute, I think, again, I don't think it takes a degree in statistics to pick out the errors on this one. They kind of jump out at you, right? So we have 2 effect sizes. These are Cohen's d effect sizes. Even harder to get a Cohen's d to be large, because it's between group rather than within group. So Cohen's d of 5 and 7, highly unlikely values. And you can see that both of these effect sizes are completely pulling the pooled estimate to the right, from all of the other estimates. This one in particular gets pulled to the right. We went back and checked the underlying papers, and sure enough, what happened was these are errors. Somebody put standard error rather than standard deviation into the effect size calculation. But these kind of, should jump out at you, right? I think that they're really, somebody should have caught it. When I see stuff like this, it makes me wonder, is anybody even reading these papers? Kind of thinking back to James Heathers' talk this morning, where he's talking about the problems with peer review. That really resonated with me, because sometimes I do wonder, did the journal editor look at the paper? Did the peer reviewers actually read it? Is anybody reading these papers, right? Because the errors are so obvious that they really should jump out at you. And there was more examples. I'll show you a few more of the papers that we found in the literature. So here's another one. One of the most highly cited meta-analyses in strength and conditioning research. Again, if you look at the forest plot and you see one of those effect sizes seems implausible, seems very different than the others. Indeed, this one right here, the effect size is the Cohen's d as well of 4. That is an error. Again, same error, use standard error rather than standard deviation, but again, really should have jumped out at somebody that it was really different, and again, completely pulling the pooled effect size to the right. Another one, again, another one that I think should have jumped out at people. These are, highly cited, published meta-analyses. You can probably pick out the 2 that are wrong. Effect sizes of 3 and 8, same error. Standard error was used rather than standard deviation. They're completely pulling the effect size, in this case, to the left. It's from the same paper, effect sizes of 6 and 11.8. Highly implausible effect sizes. These are Hedges G's. Again, same thing. In fact, we went through and counted up like all of the effect sizes, either Hedges G or Cohen's D, that were 3 standard deviations or greater. The majority of those were due to this error. So if you are reviewing meta-analyses and you see effect sizes of 3 or greater, that should be a red flag for you that they may have an error. All right, one more example that I just caught. I know Nick Tiller is giving a talk that I'm looking forward to tomorrow, so maybe he's going to talk a little bit more about this example, but I just saw his thread on Twitter. I thought it was worth mentioning. I'll refer you to the thread to read more about it. But this was a very interesting case, a good outcome in some sense, because Nick wrote a letter to the editor, and actually that paper got retracted amazingly quickly. But this was another example of a paper where the effect size was implausible at face value. Not a meta-analysis, this was just an original research paper. But they had randomized, these were twin pairs, and one of the twins got vitamin D, and the other twin got nothing. There were no other changes to routine. The authors even said there were no changes in the level of physical activity. It was 60 days of supplementation. You look right in the abstract. This is not even buried anywhere in a figure or a table. It's right in the abstract. It says cardiorespiratory fitness improved after supplementation through increases in the values of maximum oxygen consumption, VO2 max, of 28%. Now, that should jump out at you as being highly, highly implausible at face value. There is no way that vitamin D supplementation improves your VO2 max by 28%. If that were the case, every athlete on the planet would already be taking vitamin D because it would be so obvious that there was an effect there. For a benchmark, things like performance enhancing drugs like EPO increase your VO2 max, maybe 7 to 12%. So this is just not, it's just ludicrous at face value. Don't get me started on the whole vitamin D increases your VO2 max narrative. That's another nonsense story. But we'll save that story for another day. Obviously, there's a big confounder there, exercising outdoors. Anyway, this is a really good thread because there were a bunch of other red flags in that paper, as Nick talks about in his Twitter thread and his letter to the editor, but it was sitting right in the abstract, something just highly implausible. And it makes me think, are anybody reading these papers, right? How did this get through peer review? At least that one got retracted. All right, so that brings me now to my wish list for improving the statistics in sports science. And I published an editorial by this name with Karim Chamari in IJSPT back in December. So I'm going to talk about some of the items in that editorial, but I've added one to the list, the very top of the list. So when we were writing that, we were thinking of items where you might be able to shape journal policy around them. So we didn't put the first one on the list because it's hard to imagine, mandating thinking, although I wish we could. But high on my list of, things I would like to see improved in not just sports science, but across, all scientific fields, is thinking, right? Using critical thinking and avoiding brainless statistics. So all of those errors I just talked about arose because people weren't paying attention. They weren't bothering to ask just really basic, simple questions about what the numbers mean. If we could do better on that first one, I think that would save us a lot of, get rid of a lot of the errors, the types of errors that I see. So think, use common sense, ask basic questions about what the results mean and whether they make sense. And a lot of doing this part right does not require a degree in statistics. You just have to be able to look at basic numbers, ask basic questions. And I think part of the reason so many things go wrong in statistics is because people get intimidated by statistics and they don't feel confident in their own ability to, look at statistics and make sense of it. So have a little more confidence, right? All of you could have caught those errors that I just showed you. They didn't take a degree in statistics. The other thing we need to do is to avoid statistical cookbooks and bandwagons. Unfortunately, a lot of the way that statistics is taught to applied scientists is by a cookbook fashion. And I think that encourages a lot of blind and brainless statistics. I'm also a big advocate of using simulation to understand how statistics work. I don't have enough time in this talk to talk a lot about this, but in some ways, simulation is the antidote to cookbook statistics, because if you learn to do a little bit of simulation, you can really start to understand how models work. Another fun example of brainless statistics from my archives. I changed it a little bit, but this is based on a real example, a real paper that I was reviewing last year. This is not from sports science, so just to show you that not all, all of the things I'm talking about today apply to other fields as well. This was looking at predictors of heart attack, myocardial infarction. And this was one of their tables where they were putting the odds ratios from logistic regression. And if you look at these odds ratios, they're kind of fun. We get odds ratios of 1,018. I love how there's, 1,018.49, as if we need to go out to 2 decimal places of precision in this case. Obviously, these are meaningless, ridiculous odds ratios. How does this creep into a paper? Well, somebody dumps a bunch of statistics into the black box of the computer, presses some buttons, out comes some output, and you just stick the output into your table without thinking about it. That's obviously what happened here. Probably what happened is the computer, sort of by default, chose the lowest age group as the reference group. 0 to 17-year-olds, guess what? They don't have many heart attacks. So maybe there was one event, one heart attack in that group. If your reference group has only one event, then all of a sudden that's going to blow up all of your odds ratios and make these kind of useless, meaningless odds ratios. That could be avoided if somebody was just paying attention and thinking about what the numbers mean. Again, avoid statistical cookbooks and bandwagons. So I think, unfortunately, because people often feel, unconfident or intimidated by statistics, they reach for a statistical cookbook, hoping that somebody can tell them, well, if you just do X, Y, and Z, then you'll get it right. That is the worst way to do statistics. You should never be doing something in statistics just because somebody told you to do it that way. You need to understand what you're doing. Same thing with statistical bandwagons. Things become trendy, and then everybody goes, oh, yeah, I'm on that trend, even though they may not really understand any of the arguments. So we want to avoid that. You want to always understand what's going on under the hood when you're doing statistics. I'll just give one example from sports science of statistical cookbooking that I've seen. Some of you may know that I spent some time criticizing the method magnitude-based inference, which was popular for a while in sports science. And, I spent a lot of time criticizing the methodologic, underpinnings of that method. But there were also just some practical issues because the method was sort of presented as a cookbook in Excel. You could just dump your data in, press some buttons, and something comes out. And so when we were reviewing a lot of the papers that use that method, we noticed that the statistical method section was basically like a cut and paste across different papers. It was kind of verbatim, the same language. And one of the sentences that really jumped out at me, because I kept seeing it, and it's not a standard term, which said all variables were log transformed to reduce bias because of non-uniformity of error. And so non-uniformity of error, I've never seen that term used anywhere else. So that's why it kind of stuck in my head as I kept seeing this sentence over and over again. And you can see that it's basically the same sentence cut and pasted. And I'm sure that these authors probably didn't actually do any data checks to see, whether this assumption was violated or not. I think the non-uniformity of error is referring to the non-homogeneity of variances assumption. And I bet you, though, if you ask the authors of those papers to explain what that sentence means, they'd probably have a hard time doing it. They're just log transforming because somebody told them to, and that's never a good reason to do something. Log transformation takes you away from the original units, which makes it easier to make errors. So we shouldn't be blanket log transforming. The funny thing also is I think this is about the homogeneity of variances assumption. All of these papers I'm showing you here were either crossover studies or they used equal sample sizes in the different groups. And the homogeneity of variances assumption doesn't matter if you have equal sample sizes in the groups. So not doing things, we really shouldn't be doing things blindly just because somebody told us to. I think simulation is the way to actually understand what you're doing. And again, I don't have time in this talk to go into a lot of detail on simulation, but if you're going to be using a model, just even a linear regression, a t-test, an ANOVA, repeated measures ANOVA, a mixed model, whatever you're going to be analyzing your data with, if you're going to be performing your own analyses, you can simulate data that looks a little bit like the data that you're going to be using, but you understand exactly what's going on in that data because you simulated it. So you know the distribution, you know the effect size. You can then see how that translates into the output of your model. You can see the one-to-one correspondence that helps you to understand what the model is doing. You can also do things like, hey, I'm going to generate some data where I know I have failed to meet the assumptions of the model. I'm going to generate non-normal data or data that violates homogeneity of variance or data that's correlated. And then I can see how that affects the model and when those assumptions matter and when they don't. It's a really good way to get your head around how these statistical models work. And I know it sounds like something that must be hard to do. It's actually not. Like I teach probability. Probability is hard. Simulation is actually fairly straightforward with just a little bit of code. So it's something that you really should think about if you're going to be doing your own analyses, trying to learn. All right, second item on my wish list, collaborate with a statistician or related methodologist. I'm a big advocate of having statisticians involved in research teams. Obviously, there's a lot that a statistician can do for you. I think we often focus just on the data analysis step. I'm frequently asked to help on a project after the data are already in. Hey, I've got some data, can you analyze it? But I just want to point out that statisticians can help all along the study pipeline from study planning, sample size, all the way to the presentation of the data. And the one I want to focus on today, just because it's the one I think that's underappreciated, is that statisticians can help a lot with data processing and cleaning. It's not a glamorous step, but I'll tell you that about 90% of what I do as a statistician is data processing and cleaning. And it's super, super important. I've had, working with some groups over the past few years, have had several cases where somebody would, ask me to help on a data analysis, and they'll say something like, "Oh, we've got some data. Can you help with it? Oh, but the data won't be ready for like 2 months. We need the graduate student to do something to the data first." And I was like, "Wait, what do you mean?" Like the data are collected, so. What I realized a lot of people are doing is like having your grads, I know we have to keep grad students busy, but it's not a good use of their time, is that having a grad student go in and like manually calculate risk scores for people in the data set. Or I had a situation where they had built this beautiful online food frequency questionnaire where they were asking about, specialized food intake and also energy output. But they were manually coding all the nutrient values in Excel. And I was like, no, you don't need to do that. Give me your algorithm and I can write code to process the data, which is going to improve reproducibility. It's going to improve consistency. And also it's going to avoid errors, and not to mention the time saved by the poor grad student. So just to give you an example, this is the code that I wrote for the food frequency questionnaire. So it takes a couple of days to write code like this. But once it's done, you now have a complete record of exactly how all the variables are calculated. And all you have to do is just run the raw data through this program, and out comes all the variables you're looking for. So, just keep in the back of your mind that that's another thing a statistician can help with, is to avoid any kind of manual data processing, which you should never be doing. All right, point 3, sharing data and code. So I feel like I'm sort of preaching to the choir on this one, since this is the STORK conference. I assume that you are all on board with sharing data and code. For me, I do a ton of statistical review, and my life would be a lot easier if everybody shared data and code. So that's my plea to you to share your data and code. I usually spend on a statistical review at least one round of review and revisions in which I am just trying to figure out what you did to your data, because statistical method sections are usually fairly impenetrable. They're hard to read. It takes me one round to kind of figure out even what you did before I can even evaluate whether I think it's the right thing to do. If you give me data, I also am able to check it for you. And it's a good thing if I check your data and find errors. You want those errors to be found before they are published. There's empirical evidence, though, that we are not doing well in sports science in terms of sharing data and code. And again, this is not in any way unique to sports science. I think if you queried other fields, you would find something similar. But David Borg did a review in 2019 of 299 articles from top sports science journals. He found 4.3% that had actually shared the data, and an additional 1.7% that stated the data were available upon request. James Heathers talked about that this morning with what that really means. Does that mean you actually can get the data? Often not. And then 0% had shared code, nobody. So obviously there's a lot of room for improvement in this one. And this one's hard to change culturally. When people are used to not having to do something, if you ask them to do an additional task, they usually don't like to have to do an extra task if they've never had to before. So this one is going to have to be changed, through journal policy, because currently there are no incentives for sharing your data and code. Journals have to build in those incentives. And I have to say this, the real way this is going to change is generational. So it's going to be all of you who are young who are going to change the culture, because you're actually going to share your data and code. We're not going to get the old fogies to do it. All right, 4th item on my wish list, sample size. So I've heard some of the speakers today talk about the issues with sample size in sports science. I think sports science is a little bit notorious for having pretty small sample sizes. So we need to do a better job in sample size planning and sample size. Again, empirical evidence, and I think we saw some in some earlier talk today, also some papers looking at how often are sample size calculations included in papers? What are the sample sizes? So there was a good editorial out in 2020 in the Journal of Sports Sciences, and they looked at 120 papers from their journal. They found that only 11% included a formal a priori sample size calculation, and the median sample size was just 19. And then I was recently involved in a review specifically of reliability studies in sports science and rehabilitation. And we found that only 9% had an a priori sample size calculation. The median sample size was 18. So clearly a lot of room for improvement here. I'll just put a little plug in for doing sample size for reliability studies. So what's the point of a reliability study? It's usually you're trying to estimate the reliability coefficient, usually either the kappa coefficient or the ICC. If you have a very small sample size, you may end up with extremely wide confidence intervals around your estimate, and you may end up with something useless. And so I was just reviewing a paper the other day where they were using kappa. The 95% confidence intervals for the kappa went from like -0.1 up to 0.97, something in that range. So that is useless, because it's basically saying that any reliability, any amount of agreement is plausible, anywhere from no agreement to perfect agreement. So that's kind of a useless result. So you really need to make sure you have a big enough sample size that you can precisely estimate reliability. And I'll just put in a plug for the paper that I just did with David Borg and PMNR, where we were trying to give resources for researchers to actually calculate sample size a priori for reliability studies, which, as we said, I said is not often done. And so we provided some code and some lookup tables to try to reduce the barrier to entry there, since there's a lot written on sample size for randomized trials, but not much for reliability. All right, my fifth point, my fifth wish list item. When I review papers, I kind of feel like a broken record recently. I feel like there's two comments I make in almost every review I do. So this might reveal if I've reviewed something for you recently. But one of the comments actually is not statistical, but one of the comments I keep making over and over again is, please stop using so many made up acronyms and abbreviations, because those drive me crazy as a reader. People will, instead of writing outpatient and inpatient, they will write OP and IP, and I'm never going to remember those abbreviations. Just write outpatient and inpatient, please. And then the second comment that I find myself writing over and over again in review is, if you have put a regression model or a correlation matrix into your paper, I need to see plots that give me some sense of whether or not those relationships are robust and whether or not they're real. So I find myself writing that comment over and over again as well. The reason I need a data visualization is it allows me to assess a bunch of really important things, like the model fit, the model assumptions, how robust is the relationship. Especially important with really small samples, there's a risk of outliers driving an entire relationship, and there's risk of overfitting. So I really like to see those data visualizations. And just as a hypothetical example here, this is some made up data, but just to give you a sense of what I'm talking about, I've based this on a few real examples that I have seen in review. So this is based on real examples, even though the data are made up. But imagine we've got a longitudinal study of runners with bone stress injuries. I spent a lot of time on data on bone stress injuries. And we have sample size, say 46, and they're looking at the outcome of time to recovery. How long does it take you from the diagnosis of the injury until you're able to run again in days? And looking for predictors of that. So you can imagine a study like this, you might see a table that looks something like this, right? This is your sort of standard regression table in the paper. The outcome, again, is the recovery time in days. And if you look at the table, it looks, kind of impressive, right? So more vitamin D, more bone mineral density, those things are related to faster recovery with 8 p-values. And your MRI grade and the presence of hormone deficiency are positively related to higher recovery times. Again, look at that p-value, right? Very exciting. And you can imagine the authors getting those results and kind of going, wow, okay, great. We have this great story, lower vitamin D, lower bone mineral density, higher MRI grade, hormone deficiency. All of those things are going to mean that you take longer to recover. The problem is that I don't know from just looking at this table whether these results are real or not. In other words, you could have very non-robust data that produce these results, as I'll show you in a minute. And there's a few clues in this table, and again, I'm basing this on a couple of real examples of things I reviewed. There's a few clues in this table that maybe things are not so great. So for example, if you look at the beta coefficient, this gets back to thinking and thinking about what numbers mean. Just look at the beta coefficient for hormone deficiency and think for a minute about what it means. So the value here is 236, and that's days of recovery. This is a binary predictor. So that would be saying, basically, if you have hormone deficiency versus you don't, we would expect you to take 236 days longer to recovery. Now, if you know anything about bone stress injuries, that is way outside the range of recovery times. In fact, in this made-up data set, which I based kind of on real data, the median recovery time was 76 days. So this immediately is going to jump out at me as like, something's not quite right. I'm immediately going to suspect when I see something like this, that there maybe are just 2 people who have hormone deficiency. That can drive a beta coefficient like that when you have very few people, and maybe one of them has a really high recovery time. So that's what I'm going to suspect. I can't confirm that until I can actually see a plot of the data. Another little clue here, tucked in the footnote, the R squared is 80%. Okay, that is too good to be true. We are not explaining 80% of the variance in recovery times. It's way too complicated. So that is a little clue to me. Like, you might look at that and say, wow, I have a great model. I look at that and say, wow, you've overfit your model. The other thing tucked in, and again, this is based on some real examples of things I was reviewing. One time I was reviewing a paper where they had just like cut and paste all the extra little statistical information that comes out in your statistical output into the table. Now, I appreciated seeing it, although it was kind of funny having it in the table. But one of the things that came out, it was like, the number of observations used in the model. And I suddenly realized, oh, half the data was thrown out. So when you do a multiple regression model, if any of the observations are missing data on just one variable, they're going to be booted out of the model. So all of a sudden, I see this all the time where you have half of your data is thrown out, and sometimes people don't even realize it. And so that's obviously problematic if you're losing half your data. So a couple of red flags in the table on that one, but I'm going to ask to see the plots. And again, these are made up data, but these data actually generated the table you just saw. So I'm plotting here the recovery times against vitamin D. Well, hopefully it jumps out at you very quickly. Oh, wait, we have an outlier. With a small sample, an outlier can drive a lot of relationship. And so there's somebody with a recovery time of over 500 days. I'm immediately going to suspect a data entry error, or this is just a really weird case. But that's driving the relationship almost completely, as you can see here with vitamin D. If you got rid of that person, there'd really be no relationship here. So that relationship is not robust. And then we look at this is bone density Z-scores. And again, we've got that one outlier plus another, let's say it's a data entry error, those two completely driving that relationship. Otherwise, there's nothing there. MRI grade, mostly being driven by that one outlier. And then hormone deficiency, indeed, there were very few people who were deficient. So there were 3. One of these data points got thrown out of the model because they were missing data on the other 3 variables. So actually that beta coefficient I showed you with a really nice p-value, that was based on 2 people, one of whom just happened to have a really high recovery time. So all of this is going to tell me that this is not a robust relationship. Actually, you as the author looking at the plots should realize, hey, this is not a robust relationship. So I'm always going to ask to see those data behind the scenes. Little tip for those of you who are young investigators getting ready to do your first paper, respond to peer reviewers. Be careful when you respond to peer reviewers. So this is how not to respond to a review request. So recently I wrote my little comment, I need to see the plots to go along with the regression model. And the comments I got back from the authors were, we checked the graphs and they were correct, and it is not possible to attach them. And I was like, wait a minute, of course you can send me the graphs. And they were correct. It's not a correct, incorrect situation. It's me wanting to judge like the fit of the model. And also, I'm not going to trust that just because you said they were correct, that I'm going to think so. Anyway, that paper got rejected, so don't respond to peer review that way. All right, so the final thing on my list that I think is particularly pertinent to sports science, again, not unique to sports science in any way, but a problem that I see that's not well addressed in sports science is worrying about multiple testing. It tends to be that the sports science papers I've seen have lots and lots of outcomes. So I was involved in one review of over 200 sports science papers. We looked at the number of statistical tests that were run that were just related to outcomes, and the median number was 30. That's a lot. So that's like, you know, maybe I looked at 15 different outcomes at 2 time points, right? That really increases your chance of making a type 1 error if you're looking at so many outcomes. Only 14% of those papers identified a primary outcome, although most of these were randomized trials. And there was little use of formal corrections for multiple testing. Very few cases when people had multiple time points did they use an appropriate model for repeated measures, which helps control your type 1 error. So a lot going on that really got me worried about multiple testing. I kind of think of your typical sports science paper. I'm being a little facetious here, but like this is, you know, maybe I'm exaggerating a little, but you know, we gave 12 people an intervention. We measured 30 outcomes. We found something interesting, however you define that, in 2 outcomes. And therefore, we think the intervention works in those 2 outcomes, right? That's a little bit of what I feel like a lot of the sports science papers look like. And of course, there's a huge, huge type 1 error problem there. So some things to think about with regards to multiple testing. If you're doing an intervention trial where it has to really be planned ahead and hopefully you're pre-registering, designate a primary outcome. So that's one way to control type 1 error, is to just have a designated primary outcome. Then you've controlled the type 1 error on that outcome. And you know, everybody understands, then you can throw in a lot of secondary outcomes, but everybody understands that the type 1 error rate is higher for those. So that's one option. Again, underused in sports science from what we've seen. You can also think about using composite outcomes. I haven't seen this as much in sports science, but that's a way to reduce the number of outcomes that's used in lots of other fields. Certainly, if you have multiple time points, you don't want to be comparing the groups at each time point with a different test. You want to use a model that accommodates repeated measures. And then there is the option to formally correct for multiple testing. So maybe you do want to look at 10 separate outcomes. You don't want to make a composite outcome. You don't want to designate one as primary. You always have the option of doing that formal correction for multiple testing. And I'm going to say just a bit about the fact that there's much, much more than Bonferroni. This is an area maybe where collaborating with a statistician can help. For observational studies, I don't necessarily think we need to do any formal corrections for multiple testing. What I'd like to see in observational studies is that authors put everything in context and be transparent, right? So if you looked at 60 different outcomes, telling your reader that is really helpful, and putting in context, right? Something like we considered 60 different outcomes, and thus the 3 significant results we found are consistent with chance. So just letting your reader know that that is consistent with a picture of chance, rather than making this big story about the 3 significant results. I wished I'd see, like, that to me would be a perfectly acceptable way to deal with multiple testing in an observational study, but I, again, don't see that very often. All right, I'll just put a plug in that there's a lot more than Bonferroni, and so another reason to collaborate with a statistician. I think everybody's familiar with Bonferroni, so it looks something like, okay, I have 10 outcomes, and I want to control my family-wise type 1 error rate at 0.05. So in Bonferroni, I'm just going to take the 0.05, I'm going to divide by 10, my new threshold becomes 0.005. So I think most people have seen that one. It's very simple, and I think that's why it gets widely used, because it's easy to implement. However, as you might have heard, Bonferroni is over conservative. Well, what do we mean by that? So just to kind of get you thinking in terms of why the Bonferroni test is overly conservative, I've shown here, this is a made up correlation matrix, obviously, for 10 outcomes that you might see in sports science. And I've obviously made this one up because this is a correlation matrix with Pearson's correlation coefficient. And I'm saying that there's no correlation between any of these variables, right? So no correlation between vigor and fatigue, no correlation between 2 different measures of CMJ, right? This is obviously highly unrealistic, but this is what Bonferroni is assuming. And so in terms of multiple testing, if you use, sort of the standard 0.05 alpha, and call things significant if they meet 0.05 without any correction for multiple testing, if you have 10 outcomes and they're all independent, you can show that your chance that if there's really nothing going on in your data, there's no association, your chance of finding at least one significant, that is under 0.05 association just by chance, is about 40%. We call that the family-wise type 1 error rate. So that gives you a sense of like, hey, if I look at 10 outcomes, I'm really likely to find one significant one if everything is independent. But the real world in sports science is probably something more like this. Again, this is an artificial matrix. Correlation matrix, obviously, real data is going to be a little bit more complicated than this, but imagine that instead of having no correlation between all these variables, I have some moderate correlation, say Pearson's correlation of 0.6. This is more realistic for what we deal with in sports science. Interestingly, this is a good question, like I put on exams for my students. How does that affect your family-wise type 1 error rate? Well, turns out if you were to not do any correction for multiple testing, and you used, again, that cutoff of 0.05, and there was nothing going on in your data, you would only have a 26% chance of at least one of those meeting that 0.05 threshold. So it's actually lower than if they're all independent. And you have to think about that a little bit, but it's because the variables are moving in the same direction. So if you have it's like there's less opportunities for chance fluctuation because they are moving together. So there's other alternatives to Bonferroni that take into account this correlation structure. So one I'll just point out, because actually I think it's actually really simple to implement, even though it might sound a little complicated, it's actually fairly simple to implement, is the M-effective method. And it looks very similar to Bonferroni. But instead of dividing by the total number of outcomes, say the 10 outcomes that you looked at, instead you divide by the effective number of independent outcomes. So maybe you looked at 10 outcomes, but once you account for the correlation between those different outcomes, maybe effectively you only have 6 independent outcomes. So you divide by 6 rather than 10. So I think conceptually this is pretty easy to understand, and calculating that effective number of independent outcomes actually is pretty straightforward as well. And there's various ways people have proposed for calculating that, but they're all related to just the correlation matrix. I don't want to scare anybody with linear algebra here, so I'll show you how this is calculated on the next page, just to show you that it's not complicated. But based on the correlation matrix, you can come up with this number. And just to give you one calculation example, if I have a correlation matrix that looks like this, all moderate correlation, I can ask the computer to calculate, this is called the eigenvector, the set of eigenvalues that go with that correlation matrix. If you haven't had linear algebra, don't worry, this is something that's actually pretty easy for the computer to calculate. I don't remember how to do that linear algebra 25 years ago, but my computer can do that math for me without me having to remember how to do it by hand. So I get, basically, this is a summary of that correlation matrix. And in this particular way of calculating the effective number of independent outcomes, I'm just taking the variance of these values called the eigenvalues and plugging them into this equation. Comes out to 6.75 here. In other words, I have 10 outcomes, but because they're correlated, I effectively have only 6.75 independent outcomes. So I can then just divide my 0.05 by 6.75, and I end up with a less stringent threshold. So just want to point out that there's, put in your mind that there's these other methods out there besides Bonferroni. All right, so that brings me back to my wish list. Of course, that first one, just thinking, avoiding brainless statistics, in my mind, the most important, but getting involved with a statistician, also really, really helpful. And I am going to open it up now. We've got left like 3 minutes for questions. So hopefully we have a few minutes for questions here.
Thanks a million, Kristin. Some awesome advice there. We do have if you have a few moments, we do have a few questions coming into the
great,
chat
yes.
here.
I haven't been paying attention to the chat, so I can't now. Yeah.
So let me see, where does it start?
James, these seem such obvious and basic errors. How did they get past the reviewer or editor? I really do think, like, is anybody reading these papers? I have been sent some papers for review this year. I almost put in this talk because they were so ludicrous. Which I wrote back to the editor, like, are you kidding me that this wasn't desk projected? I literally, I'm getting older and more cranky. So, I've had some nasty notes to editors who sent me things that should have been desk projected. Yeah, that standard error. As others of you have seen that standard error, standard deviation mix up. Yep.
Unfortunately,
our evaluation, this meta-analysis evaluation that we did is in review currently. Actually, it's on my to-do list to respond to reviewers. Haven't had a chance to do that yet, but it is in review, so hopefully that will be out soon. And let's see. Yeah, links. It looks like Vanessa's taking care of links. For calculating the required sample size, often a priori power analysis is used. However, sometimes prior effect sizes are not available to do this. Other times people do a priori power based on pilot data. What do you recommend? So one way to do a priori power, if you don't have pilot data or you don't have a sense of the effect size, is to think about what is the minimum effect size I would care about, right? So you can also power things around, like, if it's smaller than this, I don't care about it anyway. So I need to have a sufficient sample size to find, like, an amount that I would care about. Presumably, that would have to be something that you've measured before, so you have some sense of what a big enough to care about is. But sometimes we have that even when we don't have pilot data. Oh, and yes, I think we're putting references in the chat. I have more references for that, and so feel free, of course, to email me or send me a message afterwards if you want any of those references. I have a lot more references than I put in the slides, I think. Good. Other questions? If anybody wants to unmute and just jump in and chat, I'm happy to answer questions. Yeah, Yeah.
Can I ask one? I was about
Yes.
to ask I was about to type another one in the chat. When you mentioned composite outcomes, how would you go about creating them? I'm dabbling with a factor analysis at the moment. I'm not personally doing the statistics because I don't know how, but it seems like quite a complex thing to do. And I was just wondering, do you have any advice?
Yeah, well, they're done in all sorts of ways, probably some better than others. Sometimes they're done, I was just doing a lecture about composite outcomes, and sometimes they're done just, expert opinion, right? So it can be as simple as that. And sometimes it's data-based. So you might be doing factor analysis or principal components analysis. So you have to decide which of those makes the most sense for your application. Sometimes composite measures have been validated previously. That's the best case scenario. I don't think there's a lot of those in sports science, though. So you're probably going to have to do some work.
Okay, so there's a couple more.
Yeah, my email. I'm kcobb@stanford.edu. I'm going to put that in the chat now. Feel free to email me. And let's see, we have one more question about errors in meta-analysis. What is your opinion on the most effective approach, e.g. individual letters to the editor or broader review paper? What is the best way to notify readers of these errors? That's a great question. I think Nick is talking about that. What somebody tomorrow is talking about. I saw that on the talk list.
Sam Orange.
There's no good answer to that one. What I tend to do is a lot of errors that I detect, I end up writing a teaching article about it. So rather than criticizing individual people or articles, I write a general thing and use it as an example. I feel that people generally are a little bit more receptive to that, unless it's an error that really makes a difference, like somebody is selling a product, or that the method is being used in many papers. Then I might be a little bit more critical and try harder to get something retracted or openly criticized. But I do a lot of more teaching examples. If it's just some paper that maybe is not going to have a big impact, use it as a teaching example to tell other people not to do it, but without necessarily getting into trying to retract the paper or things that are more tricky and difficult.
Sorry, can I go back to one question I had?
Oh, sure, yes.
Earlier, I think we missed it on the way down. One thing I'm noticing a lot in meta-analyses when extracting is unusually implausibly large effect sizes, but I'm double checking, it's not standard error, not standard deviation. Keith actually replied there and said he's seen the same thing, unusual skew in the population.
We encountered this in the review that we did. Some of those effect sizes that were 3 or greater were not standard error, standard deviation mix up. And we were like, well, there's something else going on, right? Yeah. So we weren't, the purpose was not to figure out what else was going on. So we kind of threw up our hands and said, yep, something is weird here, but we can't necessarily pinpoint it. So that, of course, there's a litany of things it could be, right? There could be other errors in the data that are not recognizable, like that without having the underlying data, you just don't know. Could be fraud, right? I mean, so there's lots of potential explanations. We didn't probe into that, but we definitely came across some of those where we did not believe the effect size, even though it was certainly, we could prove that it was not a standard error, standard deviation mix up. So there are other errors probably running around. I'll leave that for somebody else to figure out.
Have any thoughts on, if you're conducting a meta-analysis, you spot that it seems unusually large, but we can't pinpoint the reason? Do you exclude? Do you go ahead? Do you?
I think it's worth thinking about, how does that affect your meta-analysis? How does that affect your pooled estimates? And if I'm reviewing a meta-analysis with a weird effect size, I'm certainly going to say, pull that original paper and look again and think about it carefully. Yeah.
I think Paul has made a pertinent comment there, a general problem with restricted sampling and low standard deviations.
Yes, right. So the standard deviations could be abnormally low. We saw a few of those in the the review where we did not believe the standard deviations were as low as they said, and we don't know why that, but implausibly low standard deviations for sure. Yeah. Yes, you can run the meta-analysis with and without it, Vanessa. I'm a big believer in, trying with and without and seeing how much it affects it, so you have a sense of the potential impact. Yeah.
So the difficulty sometimes is when it's a kind of a sliding scale off. These are definitely too big, but like, where do you put your line?
Right. So I would say, definitely effect sizes of 3 and up you should always be very, very skeptical. I don't believe that most of those are real. Yeah. And obviously we found that the majority, in fact, are the standard error. So we can explain the majority of them. The others, I couldn't explain, but still don't believe. Yeah. So
when do you add them or keep them in the analysis and then explain them in the paper? Because I feel like if you just like throw them out, then they
No, I don't believe in throwing data points out either and just pretending they don't exist. So yeah, you run it with and without and report both sets of results, and you let your reader make judgments. Yeah.
Got it.
Sensitivity analysis. Yes. Yeah, exactly.
Nice. Kristin, I'm conscious of your time and we're running over
I'm
now.
out of time here, yeah.
Well, look, I'll stop the recording anyway.